It's my great pleasure to present our guest, our speaker for today, Professor Nazaikinskii from Moscow. And I don't see title of his talk, but probably he will tell his title himself. It's our great pleasure to have you at our seminar. Thank you very much for agreeing to deliver a lecture at our seminar. And please go ahead. Thank you very much.
Yeah. Thank you very much. It is a pleasure for me to give a talk at this seminar. Today I will speak about semiclassical asymptotics on stratified manifolds. In fact, not an arbitrary stratified manifolds, but on stratified manifolds of a very special nature, but nevertheless. And maybe I will start with two examples of problems which lead to the necessity to consider the class of semiclassical asymptotic and stratified manifolds, which will I talk about. The first problem is the shallow water equations in a basin with shallow coast. So let me have some domain D, which represents a basin of, say, of water. And we have here the depth function d of x, which is c infinity of the domain d. Maybe not very good notation, but so whatsoever. D of x is 0 on the boundary, and the gradient of d is non-zero on the boundary. And the linear approximation, the water waves in this basin can be described by the shallow water equations of this sort, minus d over dt square plus nabla d of x nabla eta is 0, and well, some initial conditions.
Sorry, some technical problems.
Well, okay, but I hope you still hear me and see my presentation.
Yes, we see perfectly. Thank you very much. Sorry for that.
Yeah, okay. So we have this wave equation for the function eta, which is the surface elevation. We see that this wave equation degenerates on the boundary. On the boundary, the function d is 0, so this wave equation degenerates on the boundary. This is one kind of equations which lead to the general constructions I will discuss here. And well, the other example is the hydrogen atom. So we have this equation. Here. X is in R3 minus I squared delta x minus 1 over the radius psi is lambda psi. And here we have a singularity at 0. The equation degenerates or has singularity at 0. So these two seemingly very different problems actually have something in common, and now I will demonstrate that. As for the shallow water equations, let's consider the simplest one-dimensional example. I can so shallow water equations. X is actually in the domain -1, 1. T of x is 1 minus x squared. So we have a one-dimensional basin with bottom of this sort. We consider waves here, and if we have steady state waves, then we deal with the eigenvalue problem for this operator p eta is lambda eta, where p is minus d over dx, 1 minus x squared d over dx. So this the generate operator. Well, so how can we construct asymptotics or exact solutions to that matter to this equation? Our idea is to reduce this equation to a non-degenerate equation on a manifold of higher dimension. Well, we proceed as follows. Consider the sphere as 2 with the North Pole, here the South Pole. Well, in R3. And on this sphere, we consider the action of the Lie group G, which is just the circle S1. And this action is by rotations above the polar axis. Well, so this is the action. And then the quotient space, this orbit space, is just the interval -1, 1. This can readily be seen. So this interval -1, 1 is just identified with the segment of the polar axis. Next, we can consider the space, say, C infinity of S2 of smooth functions on the sphere, and it contains the subspace of functions invariant under the action of the group G, and this subspace is naturally identified with the space of functions on the interval -1, 1. Well, okay, and so if we have some differential operator, say Q, on the sphere, say differential operator, and Q commutes with the action of the group G, the natural action on functions, then this Q gives rise to an operator in the quotient spaces. So say Q tilde, C infinity of -1, 1, on maybe in L2 or whatsoever, in any spaces which can be obtained by considering invariant subspaces in the space of functions on S2. And now if for Q we take the Laplace operator, then the operator Q tilde is just equal to our operator E. This is an obvious computation and well known, of course. And so the problem of constructing exact or asymptotic solutions for this equation, which has degeneration at the endpoints of the interval, is reduced to the problem of constructing exact and asymptotic solutions to the equations q psi is lambda psi, well, where psi must be G invariant. So we reduce the problem of constructing the asymptotics for equation with degeneration to a problem for an equation without degeneration, but on manifold of higher dimension, and we must seek solutions that are G invariant. This is one example, and of course, as far as the operator P is concerned, we know the exact solutions of the eigenvalue problem. They are given by the Legendre polynomials, but actually, if we use this technique and construct asymptotic solutions for the Laplace equation on the sphere and represent them by a Maslov canonical operator, then this technique gives the asymptotics of Legendre polynomials for large numbers via the Airy function. This asymptotics is, of course, also well known. It was obtained in 1918, as if I'm not mistaken, by completely different methods, but elementary method. But this is just an example. And returning to our problem for the shallow water equations in some basin D, this technique also gives a solution of the problem. We represent D as the quotient of some closed three-dimensional manifold M over the action of the group S1, and then also can construct asymptotic. This is one example, which was, as far as the asymptotics for the shallow water equations are concerned, was developed in recent years by the Brakhotov, Shafarevich, and myself. Well, and another example, which is when I return to the equation for the hydrogen atom. In fact, there is also a well-known procedure which reduces this equation to a non-degenerate equation. And this procedure is as follows. Let us consider the space R4 with coordinates U1, U2, U3, U4, and it will be convenient for me to write Z1 is U1 plus I U2, Z2 is equal U3 plus I U4. Well, here I is the imaginary unit, of course, and we consider the mapping of R4 onto R3, which of point 1, x2, x3, which is given by the following formula. Z1, Z2 is taken to Z1 times Z2 bar, the complex conjugate number, and here we have Z1 square minus modulus of Z1 square minus modulus of Z2 squared. Well, consider this mapping. I note in passing that if we restrict this mapping to the sphere S3, then we obtain a mapping of S3 to S2 with fiber S1, which is none other than the Hopf, well-known Hopf bundle. Well, and this mapping of R4 onto R3 is just the extension of this Hopf bundle mapping by homogeneity. So this mapping is, as easily seen, second-order homogeneous. Well, and so if we define an action of a circle on R4 by these formulas, just by rotations this sort, well, then we see that this mapping here, is just the projection onto the orbit space of the S1 action, and then we can reduce our equation as follows. So we consider this equation for the hydrogen atom. This equation. Sorry? Sorry, so we consider this equation. Let's multiply it by absolute value of x. So we have minus h square absolute value of x dx minus lambda x psi is equal. Here we have, sorry, it's not here. We have minus x equal to psi. You have this equation, and one can verify by straightforward computations that this operator here is none other than the restriction to the S1 invariant subspace of the following operator. Let's denote it by pi is 1/4 is minus h square, the place in the variable u, minus lambda square. So this degenerate operator here is just the trace on the invariant subspace of this operator here. This substitution was also was invented long ago in the classical mechanics by Kust and Hamer. This is as early as 1964. There were many papers about this. He called this spinor regularization of Kepler motion, and more recently, Karasev and Novikova used this representation to obtain semiclassical asymptotics for some perturbations of the hydrogen atom by magnetic field. Well, okay, so here we see two examples of how using a group action and passing to the orbit space helps one represent operators with degeneration by via traces of operators without degeneration on invariant subspaces of the group action. And so I would like to proceed to a description of the general construction and to explanation how this construction is used when constructing semiclassical asymptotics. So let's proceed to the general construction. Well, so assume that we have a C infinity manifold M without boundary, a compact Lie group G, so and we have a smooth action of G on M, Gx on M. We'll write it actually as follows. And let X be the orbit space. Then it is well known that this X is a stratified manifold. Of course, a very not arbitrary stratified manifold we construct obtained by this construction. This is very special, but nevertheless, this is a stratified manifold, and we will be interested in the construction of semiclassical asymptotics for equations on X, which are obtained from some differential pseudo-differential equations on the manifold M. And well, so if we have this orbit space, then of course we can define some function spaces on X. For example, C infinity of X is by definition C infinity of M, the subspace of infinity of M formed by G invariant functions. In a similar way, we can consider Sobolev spaces on X. In particular, the L2 of X. And so on. And so we know just by F of X a general function space obtained in this manner. General function space obtained in this manner. And so if we have an operator P at differential, pseudo-differential operator acting, say, in C infinity of M or what any other of these spaces, and if P is G invariant, then we can consider the restriction of this P to C, say C infinity of X. This is if this original operator was an H pseudo-differential operator on M, then this operator is by definition H pseudo-differential operator on X. So, well, and we intend to study the eigenvalue problem P psi is equal to lambda psi. Well, and we need to find asymptotic solutions. Asymptotic solutions are usually obtained if we have some parameter which tends to 0. But here we, of course, must have a parameter because our original operator P is, I said, is a HP differential operator, some H of X minus IHD over the X. Here, H is a small parameter tending to 0. So the operator in the subspace also depends on the parameter H, and we seek asymptotic solutions. So what is the method for seeking such asymptotic solutions? We will use the method known as Maslow's canonical operator. Maslow's canonical operator. This canonical operator is well known on smooth manifolds, and so our problem is to transfer this construction to manifolds obtained by orbit spaces of compactly grouped action on a smooth manifold. And so we proceed as follows. We will construct some canonical operator on a Lagrangian manifold lambda in T star M. And we are interested in conditions under which this operator gives G invariant functions. So what are these conditions? This is the crucial question. If we can construct canonical operator which gives G invariant function, then we can use this canonical operator to obtain asymptotic solutions of our equations on X as follows. We construct asymptotic solutions on M. These solutions will be G invariant, and hence they will define asymptotic solutions of the equation on the quotient manifold. Well, so let me recall some basics of the construction of the canonical operator, which will be needed here. So what we need to construct the canonical operator? First, we need a Lagrangian manifold. In T star M, we must have a volume form. And then if we have these objects and if some conditions known as the quantization conditions are satisfied, then we have a canonical operator, K of lambda d mu, that acts on compactly supported functions on the manifold lambda and takes them to some functions on M depending on the parameter H. Well, I will not go in the construction of the canonical operator and rather describe it as a black box. The only thing we need to know about the canonical operator, in fact, is how the pseudo-differential operators act on this operator. So there are two commutation formulas. There are two commutation formulas. The first commutation formula is as follows. If we have an arbitrary pseudo-differential operator on M and apply it to Ka, where K is this canonical operator, then in the leading term, we obtain the following. This is here, H0 is the principal symbol, principal symbol of the operator H. It is just restricted to the manifold lambda and multiplied by the function A. So in the very first approximation, the action is described just by multiplication by the restriction of the principal symbol to the Lagrangian manifold. Well, and the second commutation formula, more precise, is used if H naught restricted to lambda is 0, or maybe some constant, but we don't in this case. So let's assume it is 0. Then we have the more precise formula. In the first formula, the first term is now just 0. So we have a more precise formula in this case. Minus IH K of pi A plus O of H square, where pi is the transport operator. It is equal to the Hamiltonian vector field plus some function that, yeah, I will not write it out here. And this is Hamiltonian vector field, Hamiltonian vector field. This is well defined because if H naught, Hamiltonian vector field of the principal symbol, this is well defined because if H naught is 0 on lambda, then the Hamiltonian vector field is necessarily tangent to the manifold lambda, and so the action of this vector field on functions defined on the manifold lambda is well defined. So these are basically all the formulas we need to know to construct to find out what the invariance conditions are. Well, we will assume that the group G is connected. This is the case which is of interest to us. And if G is connected, then a function f c infinity of m is G invariant if and only if v psi f is 0 for any psi in the Lie algebra G. Here, v psi is the vector field on M naturally defined by the action of the Lie group. If we have the action of the Lie group, then to each element of the Lie algebra, there corresponds a vector field on our manifold. Well, okay. Now, v psi is the differential operator of the first order, and if we minus IH v psi is a pseudo differential operator, in fact, even the differential operator, of course, denoted by H psi, and its principal symbol, H psi, is equal to just omega 1 of v psi, where omega 1 is the fundamental one form on the symplectic manifold T star M. Well, so if let us consider the function Ka, we need it to be invariant with respect to the group G, and so it must be annihilated by all these vector fields, and so we have this by the first commutation formula. So the amplitude is arbitrary here so far, and so we must require that h psi is equal to 0 for all psi in G. So let me recall that we have the moment map that we noted by pi from T star M to the dual space of the Lie algebra, which acts by this form, exactly by this formula I of x p of psi is equal to this h psi of x p. Well, so this requirement that h psi be 0 on our manifolds lambda for each psi in G is equivalent to the requirement that our manifold lambda lies in the preimage of 0 under the moment map. Well, moreover, since the Hamiltonians h psi are equal to 0 on lambda, it follows that the Hamiltonian vector fields of these h psi are tangent to lambda, and so lambda is G invariant. Lambda is G invariant with respect to the natural action of G on T star M. Well, so, okay. And now the usual Weinstein-Marsden symplectic reduction construction shows that the manifold which I denote by L, which is the quotient of lambda by the action of G, is a Lagrangian manifold in the symplectic reduction of T star M by the action of G. I recall the symplectic reduction is obtained as follows. We take the set of regular points in pi minus 1 of 0, and then pi is just phi tilde the space of orbits. I take the space of orbits under the G action. This is a symplectic manifold. So we obtain a construction which is as follows. If we wish to have a canonical operator which is invariant, gives function invariant under the action of the group G, then we must take a Lagrangian manifold in the symplectic reduction of T star M by the action of G, and this manifold gives rise to a Lagrangian manifold lambda in T star M, and the canonical operator of this lambda is can possibly give G invariant functions. But we have only so far verified the zeroth term in the principle, the leading term, and let us use the second the second commutation formula, which is here This is the second commutation formula. Well, and here we have the transport operator pi, and for our first order operators, this q is actually 0. So the transport operator pi is just the differentiation along the Hamiltonian vector field. And now we see that the commutation formula is as follows: h psi ka is minus ih k v h psi a plus O of h square. This is the derivative along the vector field v of h psi, which is just one of the fields associated with the action of G on T star M. We need this to be 0 for all vector fields v of h psi, so A must be G invariant. And so we have a well-defined function A on the manifold L. So if A is a function of L, then we can define canonical operator on this function, and it will be invariant modulo O of h square with respect to the action of G. If we intend to obtain canonical operator which is invariant precisely, then we can just average over the action of the group G. The result will differ by O of h square from the original function, but this function will be exactly invariant. So the next steps here are to express the canonical operator on the G invariant manifold lambda via objects represented or expressible via the manifold L. Well, I don't have the time to give the exact formulas, of course, but I will just say a few words about it. First, one verifies that the quantization condition, in particular the Maslov index, are completely determined by this manifold L, and there are homology classes which occur in this quantization condition, in which are naturally defined homology classes on L. Next, one defines the canonical operator on L. It is derived from the canonical operator on lambda by integration over the orbits. And here, in the new presentation of the canonical operator, instead of the Fourier transform, one obtains some other transforms associated with some representations of the group G. For example, if we return to the problem concerning shallow water equations, then the canonical operator defined there is based on the Hankel transform instead of the Fourier transform. Of course, it is just the restriction of the Fourier transform to the subspace of symmetric functions in R2, radially symmetric functions. Well, okay, so that's basically the construction. The details will be published in a paper which is now in press in Russian Journal of Mathematical Physics and will appear in the second number issue of this year. And I would like to thank the audience, and I am ready to answer questions if there are any. Thank you very much.
Well, thank you very much for a very nice presentation, and we have time for questions, if any. You see, maybe I have one general question. You mentioned at the the start of your lecture, you mentioned spherical potentials or spherical operators. At what extent you use theory of spherical potential separators, maybe kind of calculus, fractional calculus, to establish or to find solution?
So far, this is in fact a very interesting question. So far, we didn't consider fractional calculus and didn't use it. Quite the opposite. Our aim was to reduce some problems in which you need to have some special functions to problems where you in general do not need them. For example, if you consider the equation for Bessel functions and construct asymptotic solutions to this equation by the method I have discussed, I mean for integer values of the index, then you obtain asymptotic, obtain the expression for the Bessel functions via the canonical operator on the two-dimensional manifold, and from this expression you can get all the usual asymptotics for Bessel functions. And if you have an equation with variable coefficients, then you also have such representations. But of course, there are some equations, and we are studying them, trying to study them, where you cannot use this simple procedure, and you need to use, indeed need to use fractional derivatives and all that stuff. This is a work in progress.
Yeah, I see. So I understand it's more like handling with operators rather than with spaces, right?
Yes, exactly.
Okay. Well, maybe more questions.
Yes, a general one. If there are alternative techniques for such kind of results, or this is the only possibility?
No, this is the only possibility. Quite the opposite. As far as the say the shallow water equations are concerned, we derived a completely different technique, not using this G invariant approach, and obtained all the results. But then we noticed that the use of this approach permits one to avoid proving any theorems. You see, the point is that we know very well semiclassical asymptotics in the case where there are no singularities and all the theorems are there. And if we somehow reduce our equations with singularities or with degeneration to equation without singularities, let it be on the manifold of higher dimension, but nevertheless, then we have all the theorems there. They are, well, they come with no cost at all. And then we just restrict to the invariant subspace and get what we wish. So that's basically the case. But as I, for example, for the hydrogen atom, this was done long before this general technique I speak about. And of course, I read these papers. People here didn't even mention that they deal with G invariant. They somehow used it, but this was not the point of their presentation. This was some kind of art, in fact.
Okay, thank you.
Maybe one more general question for my understanding. Somehow I thought that when you speak about shallow waters and cylindrical system of coordinates, it's better to use like kind of more cylindrical waves than spherical waves you have. Maybe I'm wrong.
Well, what do you mean cylindrical? So, do you mean one-dimensional case, or I don't really?
I mean, I'm not good in mechanics. I mean, not good in hydромechanics. But I thought that kind of motions like more than cylindrical motions than spherical. Explain
No. The spherical, the shallow water equations are obtained from the full three-dimensional equations by averaging over the vertical under certain conditions. This is possible, and then you do not all you remain with is the surface motion, the free surface elevation.
Okay.
That's also.
And you see, always when I think about sphere, I'm thinking about the powerful tool for spherical harmonics, kind of expansion people use in these cases. But
yeah, sure. Here we have some. You can have spheres of arbitrary dimension, and you will have equations with various singularities. And here we have some, kind of symmetry. You see, when you solve some equation, you can, for example, separate the variables in spherical coordinates. Yes. Then from the partial differential equation, you obtain an orderly differential equation along the radius, but this equation, of course, has some singularity in the origin.
Yes.
Here we act, strangely enough, we act in opposite direction. We start from equation which has a singularity, same in the simplest case at the origin, and we proceed to higher dimension equation, which is already partial differential equation, but has no singularities. When constructing asymptotics, when you construct exact solutions, it is easier to deal with ordinary differential equations. When you construct asymptotics, it is often easier to deal with partial differential equations, but without singularities, because when constructing solutions, you proceed to ordinary differential equations on Lagrangian manifold anyway.
Yeah, that makes a lot of.
But if your equation has no singularities, then your Lagrangian manifold will be simple, your equations will be simple, and so on. And so it is much more convenient to act this way. So this is some kind of peculiar symmetry.
I see.
The classics of science separated variables, and we act in the opposite direction. But
yes,
that's how things work.
I see. This makes a lot of sense. Thank you very much. So maybe more questions? Well, if no more questions, let's thank speaker for very nice talk.
Thank you very much.
Thank you very much, Professor Nazaikinskii, for a very nice presentation of today. And thanks everyone to participate.